Hello, my name is Jean-Francois. I'm a postdoc at the University of Oxford, and I'd like to talk to you today about measuring plume composition with emission open path FTIR. For those who may be unfamiliar, open path FTIR instruments are routinely used during volcanic eruption to measure volcanic gases. They measure the spectrum of infrared light. Traditionally, they are used with an infrared source, which can be natural, so the lava itself, or sun, in some cases the moon, or artificial with an infrared lamp. Um, Measuring the absorption of light by volcanic and atmospheric gases, this can lead to the quantitative retrieval of many volcanic gases of interest, and specifically ratios to investigate degassing processes, and which can be related to exsolution depth, among other things. One of the key restrictions of the method, however, is that it does require this specific viewing geometry, placing the gas in between a light source and the observer. And this can restrict the type of activity that can be investigated with the instrument. Specifically, it's very difficult to investigate passive degassing with the method unless there is a lava lake that can be used as an infrared source. And so in order to expand the range of applications, we've explored the possibility of using it in emission mode, where we measure the infrared light emitted by the plume itself, using the sky as a cold background. And in that case, the spectral features appear in emission rather than absorption, which does necessitate the calibration of the spectra with temperature-controlled blackbodies. This also restricts the spectral range to a much narrower atmospheric window within the thermal infrared wavelength, but it does open the possibility of quantifying particle species, in particular sulfate and ash aerosols. So we've developed a simplified forward model with a three-layer approach with the goal of developing a fast retrieval that can be implemented in real time. Once a specific viewing geometry has been defined, we obtain atmospheric profiles from balloon soundings taken at the time of measurement with pressure, temperature, and the volume mixing ratios of the gases of interest. And then using the reference forward model, full radiative transfer model, we generate spectra of radiance and transmission for two separate layers, the proximal atmosphere, which is the slice of atmosphere between the observer and the plume, and the distal atmosphere, which is essentially everything behind the plume in the line of sight. And so we allow we generate a series of runs with the reference forward model for varying levels, scaling factors for all the gases in the distal atmosphere, as well as varying temperatures in the proximal atmosphere. And then at the height of the plume, we insert a thin layer that contains volcanic species only, and for which we can generate reference extinction cross-section. So here's a quick time series of measured and modeled spectra and their misfit. As you can see, the main feature that you will see waxing and waning is the SO2, but then we have captured a series of explosions coming from the northeast and southwest crater of Stromboli when we were there in September of 2019. I'd like to draw your attention to the difference between the explosions. Here was the second one, which produced a very broad and very strong absorption that extends to the lower wave number, and the sulfate absorptions, which you will see manifest as a much gentler sloped kind of a spectral feature. The key factor here in the goodness of fit for our retrievals is how well we can model the broad spectral shape of those particle species. And so here I've plotted the variation in spectral shape of the extinction coefficient of the aerosols in greens, sulfate aerosols in green, and ash particles in gray. and how they vary with respect to their composition, their chemical composition, and their particle size on the right panel. And as you can see, the variations are relatively minor in terms of the composition, but they're much larger in terms of the particle size. And so for this reason, in our retrievals, we fix the composition of each of those species and we retrieve the particle size. Note that beyond 10 microns, those spectra look very flat indeed, and therefore retrieving the accurate size of large particles is a challenge. So when we look at the time series of the retrieved quantities, the top panel in red is the SO2, in green are the sulfate aerosols, and in gray is the ash slant column density. So during these explosions, we see that there's increases in retrieved quantities of ash that are generally associated with also high gas emissions and sulfate aerosol emissions. Outside of those explosions, there are peaks in the sulfate aerosol that do not correspond with generally with high peaks of ash, and those can be interpreted as gas puffs, perhaps like little gas bursts. There's also a correlation between the retrieved sulfate and SO2, which we can then plot in terms of the ratio between SO2 and sulfate aerosols. And so this gives an indication of the partitioning of sulfur between those two species and how it can evolve with time. So in the bottom panel, there's a time series of how this ratio evolves with time. And as you can see, there's a general trend towards decreasing ratio, which could be explained by the fact that we're entering into the night with colder temperatures. And this is, perhaps favors the formation of and the nucleation of aerosols during gas release. So I hope that I have convinced you that we have developed a quantitative retrieval for emission open path FTIR measurement. We can retrieve SO2, sulfate, and ash simultaneously and in real time. And the implications for future of ground-based monitoring are, I think, pretty significant in that it expands the range of applications of the instrument, specifically towards passive degassing. It enables nighttime monitoring as well, and it could be used to provide a measure of the ratio between sulfate and SO2 at the source, which could have a significant impact when it comes to plume dispersal modeling and VOG modeling in particular. And with this, we can investigate high-frequency variations in the emissions of all those particles and gas during persistent eruptions. Thank you.